This problem is an interesting, fun little experiment. I have a table with a hole in it. I have a puck that I place on the table. It can move around without friction, and the string goes through the hole, and I hang another mass below it. If I just hold the two masses stationary and release it, the mass underneath is going to fall downward. Well, the puck on the table is going to shoot toward the hole. They're going to accelerate. It's terrible. But if I scoot the puck sideways with just the right velocity, it'll go around in circular motion. And the tension of that circular motion is what supports the weight underneath. Another way of looking at it, the other way around, is that the tension created by the weight hanging underneath is what causes the circular motion. So that's how I want to look at it. I've drawn two free body diagrams here because I have two objects. The puck sitting on the table I call object number 1. Its weight, m1g, downward, and normal force upward aren't really of interest to the problem. What's interest to the problem is the tension T that makes the thing go around in circular motion. But for the moment, I don't know what the tension T is equal to until I look at the free body diagram for object 2, the hanging mass. Its weight, m2g, is directed downward, and the same tension is directed upward. It's the same tension because of Newton's third law, action-reaction. Because that mass that's hanging underneath is not going to accelerate, I can tell from my free body diagram that the tension directed upward must be equal to the weight m2g downward. Be careful when you do this calculation. There are two masses. m2 is the mass that's hanging underneath the table. m2 is the 1.2 kilogram mass. From this free body diagram, I can calculate the tension. The tension is equal to m2g. And then going back to my first free body diagram, I realized that the tension is the centripetal force in this problem, and that that tension must be equal to m2 v squared over r. Darn it, that's a mistake on... It's a mistake on the slide. It should say m1 v squared over r. I used the wrong mass in the slide. How about that? I'm not going to correct it. Where it says m2 there should say m1. T is equal to m1 v squared over r. And then I just solved that around for the velocity, which is rt divided by m1. So call it a learning experience. You have to be really careful how you use notation for your masses, because when there are two masses in a problem, you could easily get them confused like I just did. This is a problem about a Ferris wheel going over the top of the motion. You're sitting in one of the Ferris wheel cars and the ride is going through the top of the motion. The problem description gives you a whole bunch of data that you observe about the thing, the time period, the radius, and it asks you to calculate a few things straight off the top that you should be familiar with. It asks you for the speed, which is 2 pi r divided by the time period, and it asks you for the acceleration, which is the speed squared divided by radius. Those are two simple calculations right off the top. And then at the end of the problem, it asks for the ratio of the apparent weight to the actual weight. Well, as we've been discovering these problems, the apparent weight that I'm looking for is the normal force in the problem. Drawing a free body diagram for a person sitting in the Ferris wheel seat, the top of the Ferris wheel. Their weight mg is directed downward. The normal force is directed upward. Remember, when I do circular motion problems, that toward the center of circular motion is always the positive direction. So when I write the sum of the forces here, I'm going to write mg as a positive force minus the normal force is equal to mv squared over r. I can use this equation to calculate the normal force. The normal force is equal to mg minus mv squared over r. That's what the normal force is equal to. The problem doesn't ask me to calculate the normal force, and in fact, I think the problem may not give the mass of the rider. If I know the mass of the rider here, then I could calculate how much normal force. But it's quite possible that it's not given. That's okay, because what I'm asked for the result is the normal force divided by the actual weight. Well, the actual weight is mg. So if I were to take this normal force, mg minus mv squared over r, and divide it by mg, it would become 1 minus v squared over gr. And I don't need the mass in order to calculate the ratio of the apparent weight to the actual weight. Problem number 3 involves a car going around a flat curve. I'm skipping this one. I'm not giving it, it's the easiest one on the homework assignment. All you have to realize is that the force that makes the car go around in circular motion is the friction force. Therefore, that friction force is equal to mv squared over r. Solution done. Thankfully, the problems go on to get more interesting. The Bohr model of the hydrogen atom imagines that a hydrogen atom is like a little solar system with the proton at the center of the atom being the sun and an electron going around. That's not the way hydrogen atoms actually are. And because I have a great interest in quantum mechanics, I can't let that be. So I've included a little picture here of the way hydrogen atoms can actually look. There's a lot of different ways for them to look, and they certainly don't look like solar systems. But for the purpose of this problem, we're going to play along that an electron goes around a proton in circular motion. And they ask us to calculate a certain number of revolutions per second. I need to realize that's a frequency that they want. They want me to tell them the frequency. Well, they tell me how much force, and they tell me the mass, and they tell me the radius. So if I begin with force equals mv squared over r, I can solve that for the speed that electrons go around in the hydrogen atom. It is very, very large. It's got to be like 10 to the 6th meters per second, maybe 10 to the 7th. It is very, very, very fast velocity. So you're going to see some scientific notation here when you calculate that velocity. Once I know what that velocity is, then I know that that is equal to 2 pi r times the frequency. They gave me the radius. And so I can solve this equation for the frequency of electrons in orbit around the hydrogen atom. It is very, very high. Perhaps at some point in your life you've been on this amusement park ride, sometimes known as the Gravitron, where you get inside of a circular room and they stand you up against the wall and they spin the room and you feel stuck to the wall. Well, here's that analysis in terms of circular motion. I need to start with a good free body diagram. So here I have a free body diagram drawn for the passenger on the ride. Their weight is directed downward, and friction force is directed upward. That might surprise you a bit, but it's the friction that keeps people from falling out of the bottom of the ride. The wall of the ride exerts a normal force on the rider that is directed towards the center of circular motion. In fact, it's key to understanding this problem to realize that the normal force is the centripetal force in this problem. That is to say, the normal force is equal to mv squared over r in this solution. So, pardon me. My free body diagram gives me a bit more information, however, because looking at the diagram, I can see that the friction force directed upward would have to be equal to the weight force directed downward. And that's because you don't want the person to accelerate up and down the wall. You simply want them to have an acceleration of 0 vertically. So I'll set the friction equal to the weight. But I know more about the friction than just that. I know that the friction is equal to mu times the normal force. This set of equations that I've written here on the right-hand side lets me work out that the normal force on this ride is equal to mg divided by mu. I'm going to take that normal force and I'm going to combine it together with my expression for Newton's second law applied to circular motion. That is that the normal force is equal to mv squared over r. So what I get is that mg divided by mu is equal to mv squared over r. Notice, of course, that the m's cancel on each side, and I can solve for the speed of the ride in order for people to not fall out. That speed would be equal to the square root of gr divided by mu. Well, that's not the final answer to the question. I think the question actually wants frequency. But since the speed is equal to 2 pi r times the frequency, it should be easy enough to work that out. This next problem has a golf ball being whirled in a vertical circle. I've drawn it here in the lowest point in the motion, which is what they wanted me to investigate. So I need to draw a free body diagram for this situation, which is one that I've encountered before. At the bottom of the motion, the tension is directed upward and the weight force, mg, directed downward. When I write the sum of the forces for this, I'm going to appreciate once again that toward the center of circular motion is the positive direction. Therefore, T is a positive force and mg is a negative force. The sum of the forces then is T minus mg is equal to mv squared over r. I actually can't remember at this point what you're asked for in this problem, but now that I have my Newton's second law, it should be easy enough for me to solve for anything that I need. This problem is the most challenging problem that we've seen in a while in our physics, the conical pendulum. So I have a string, and I hold a mass on it, and I swing it so that it goes around in a circular orbit. The string sort of makes a cone as it goes around, which is why it's called the conical pendulum. Here I see the length of the string is 1 meter. The radius of the circular motion is different for everyone who does the problem, so I'm not going to be specific about that. But like all Newton's second law problems, this one begins with a good free body diagram. So I've drawn it here. The weight mg directed downward. The tension, as you can see in the diagram, is directed at an angle. Well, you know, that's no good. I have to find the components of that. There's a component of tension vertically, which is T cosine theta. And there's a component of tension that acts horizontally, that is T sine theta. You might complain at this point and say, Shelley, I get it. You're supposed to break it down into components, but they didn't tell me the angle. It's okay. You can find the angle for yourself. Because you're told the radius, and I don't know specifically what your radius is, look at the cone split down the middle as a right triangle, where 1 meter, the length of the string, is the hypotenuse, and the radius is the opposite side. I know that it's the sine function that relates the hypotenuse and the opposite side. So I simply write L sine theta is equal to R and solve it around so that the sine of theta is equal to R over L, and therefore the angle is the inverse sine of R over L. Now you know the angle. So now you can use Newton's second law applied to this free body diagram. Because the bob goes around in a circular motion, it certainly has centripetal acceleration, but it doesn't accelerate vertically. Because in the upward and downward direction the acceleration is 0, then I can confidently write that T cosine theta is equal to mg. That is an equation that allows me to calculate T. Once I know T, I can write T sine theta equals mv squared over r. If you're really clever, you'll take these two equations and stick them together, and you'll get a final result that says that the speed of a bob in a conical pendulum is equal to the square root of gr times the tangent of theta. You try to take a few minutes and be ambitious. See if you can work out that important result of circular motion.
Mm-hmm.